Welcome. In this video, we're going to talk about the queue data structure. It is very similar to the stack data structure, but instead of using the LIFO strategy, it now uses the FIFO strategy. And FIFO stands for first in, first out. So the first element that was added to the queue will be the first element to get removed from the queue. Think of a queue of people that are waiting on an event or on a ticketing machine. And you can always implement these data structures with the Python version, for example, collections.queue. This uses an advanced representation called a linked list that we'll see later. But for now, let's just focus on the basic operations of the queue. If we want to add an element to the queue, we'll call that operation enqueue, and we of course need to pass the appropriate parameter with the element we want to add. And if we want to remove an element from the queue, we use the dequeue method. Of course, we can always check whether the queue is empty, and that will be a very simple check. There are two ways that we can implement the queue, very similar to the stack, but both have a small problem with them. So first, let's see how we can implement a queue very simply with a naive implementation of a list. First, we implement the hidden list called items, and we initialize this to an empty list in the constructor. Then, whenever we want to add an element, we just append that element to the end of the list. Very easy. But then, if we want to remove an element, we need to remove it from the beginning, from the start of the list. Because we are using a FIFO strategy, we need to extract it from the 0th position of the underlying list. Finally, we can just check for whether the list is empty to respond to the isEmpty method. But let's see how this is inefficient, because it needs to move every element each time you remove an element. If we add a few elements to a list, they just get added to the end, and that's a very cheap and easy operation. But every time you need to remove one element from the queue, you need to remove the first element. And then every element after that needs to be moved one space to the left as to fill the empty blanks on the list. If instead we wanted to implement it in a different way, and let's say insert elements at the beginning of the list and then remove them from the end of the list to preserve the nature of the queue, we could just use the insert operation in enqueue and the pop operation in the dequeue, adding the 0 parameter here to the insert method. And then we could have a more efficient, or we would think, but we still have a problem because this insertion will not be fully efficient. So let's see an example. If we have this queue version 2, every time we add an element to the queue, we need to move all elements up and then to make space for the newly added element. So when the list is empty, that's very easy, we don't need to move anything. But whenever there's an element, we need to move them up and add it. And if there are more elements, then we need to move more values up the list to add the element at the beginning of the queue. Now the good part is that dequeuing elements or moving them from the queue is very cheap, because we just use the pop operation. If you remember the implementation, the pop operation on the list is very cheap, so it lets us remove elements very quickly. But we'll need to solve this issue in a future video with linked lists, which will be in the next topic of this unit. And I'll see you on the next video.